So last week we talked about different study designs and what design you should use to answer what questions, and the fact that there is no right and wrong. There's no right and wrong answer. There's no what design that is better than another. It's more about what design is appropriate for the question that you have to answer. And when we talked about the pros and cons of each designs, we introduced the notions of sample size, of bias, and of confounding as issues that can disrupt your findings and lead you to the wrong conclusions. And today we're going to go a little bit more in depth into that. If my computer works. Here we go. Okay, so let's imagine that you want to do a study that is looking at the association between use of smartphones, you know, with all the waves, etc., and coronary heart disease. Okay, so we're doing a cohort study, and we have two groups. One group that uses smartphone, and one group that doesn't use smartphone. And we look at how many outcomes we have in each group. And we find that in the group that uses smartphone, we have 2 coronary heart disease outcomes. And in the group that doesn't use a smartphone, 1. Okay, so you can calculate the prevalence or the incidence of coronary heart disease in each group. 2 out of 7 in the group that uses smartphones. 1 out of 7. You could do the odds as well if you wanted to. It would be 2 out of 5 and 1 out of 6. And then you can do, then you could do a ratio, right? You could do a risk ratio. And what would be the risk ratio in this study?
Risk ratio is 2.
It's 2. So those who use smartphones are twice as likely as to develop coronary heart disease than those who don't use smartphones, right?
Right.
It's a prevalence ratio.
It's a prevalence ratio, you're right. So do we actually believe that using a smartphone causes coronary heart disease based on this study? Probably not, right? Why?
Because the populations are not the same.
Okay.
Small.
Very small.
There might be a reason that some people use smartphones, some it might be
Exactly.
related to
You don't know.
diet,
The
sports.
period of exposure, maybe first group have been exposed for false times.
Absolutely. So many, it's a very small study. There are many potential confounding factors. We don't know how we recruited the people. We don't know how we measured the exposure and the outcome. So everything that you said can be summarized in 3 different categories: chance, bias, and confounding, right?
Mm-hmm.
And this is a really key thing. When you design a study or when you read a study, the first thing to do is you look at the results. It's like a diagnosis of exclusion that you do as a clinician. Have I excluded everything else before I can attribute the association, or whether I can consider that it's a causal relationship? So you exclude chance, you exclude bias, you exclude confounding, and we'll go through all of these. And it's the same thing when you design a study. You have to think, in the way I'm designing this, am I eliminating or reducing the possibility of finding or failing to find an association just by chance because my study is too small? Have I thought about bias in the way I recruit patients, I analyze the data, etc., etc.? And have I thought about confounding factors? And once you've gone through these 3, only then you start thinking that the exposure contributes to the outcomes causal pathway. Right? So we'll cover all these 3 things today. So let's start with chance. So imagine you have a population. Every study we do, we take a sample. We're not really interested in the sample itself. What we're interested is to infer from the sample to the population, right? Mostly that's, you know, if you're doing a study on 20 surgical patients, you're not just interested in these 20 patients. You're interested in all your surgical patients in your hospital, in Israel, across the world. So let's imagine that we have a population of 1,000 people. And what we want to know is by taking a sample, we want to know the prevalence of coronary heart disease. We want to know how many people have coronary heart disease. So we take 14 people out of the 1,000, okay? And we find that is in this sample, 3 have coronary heart disease. But actually what you don't know is how many people truly have coronary heart disease in your population. And it turns out that in your population, there's 10 people who have coronary heart disease, just purely by chance, very unlikely, but it could happen, that in a very small sample, you took 1/3 of all the people with your outcome. So you can see that the prevalence in your sample and the prevalence in your population is very different, right? So how do you know whether your prevalence or whatever outcome you're interested is a good reflection of what actually happens in the population? Well, you can do different things, and generally what you do is you put confidence intervals around it. And the confidence intervals is basically a measure of the uncertainty of your results. Yeah? And most commonly we use 95% confidence intervals. And what this means is basically that if you have a value, you say, okay, you know, and we'll see what the confidence interval is in this case. You do your calculation, you know, like, I don't know, post-surgical complication, say, you know, 2 in 50 patients have a complication. But if you extrapolate to a bigger population, you would calculate what is the smallest likely proportion of complications and the highest. So in this case, you could say, you know, if we calculated 22%, and there's a mathematical formula to calculate the confidence intervals. We don't need to go into it because it's automatically calculated by tons of software solutions. And you can even find, you know, if you type an online confidence interval calculator, you enter your sample size, and it will give you the confidence interval. So here we could see that, you know, in our sample, the prevalence of coronary heart disease is 22%, but it could be as low as 0.3%, or it could be as high as 43%.
So that means that if I take each time, 14 people out of my population, these 14, other 14,
yeah,
I can get 0.3% chance to have, I can get 43%. It's the variability.
Correct. Well,
the prevalence when I take 14 people out of my population.
It's a measure of the precision. One way to interpret confidence intervals is to say, if you sample 14 people 100 times out of this population, 95 times the value will be between these two.
Between these two.
Between 0.3 and 42.
And the other 5, it will be lower or higher.
And
okay,
it's always a result of your sample size, right? I mean,
it's
not only
a
specific confidence interval that was calculated.
We'll go into that.
Is a result of your sample size.
If something is very prevalent
yes,
or very rare, so if I understand correctly, the confidence intervals will always be narrow because you have a big chance of getting healthy 14 people or unhealthy 40 people.
Yes, so
but in the diseases that are in the middle, you can have a variability if your sample is too small.
Well, we'll talk about common, and we'll talk later about what are the factors that influence sample size, etc., etc. But you can see here that this is really not very informative to say, you know, oh, maybe almost no one in my population has heart disease, or maybe half of my population has heart disease. That's not really useful, right? If you're trying to come up with some kind of health intervention. So you need a bigger sample. And if you then went into sampling half of the population, right, which is a very large sample, you will get a value that is much closer to the reality. The bigger the sample size, the closer to the true value you get, and the narrower the confidence intervals. And you can see here that the confidence intervals are much smaller, between 0.2 and 1.3. which, if you're trying to make decisions based on this data is much more reasonable. You kind of know that it's, not that common. Whereas if you think that it could be as rare as 3 in 1,000 or as common as 50%, that really doesn't tell you anything, right? So when you look at a paper, when you look at a study, look at the confidence intervals, because it will tell you whether they've reasonably taken chance into account. Because a point estimate is not really enough.
So as much as confidence interval is narrower, there's less chance. It's it's closer to the population.
So here we're not comparing different groups. Here it's just one group.
Right.
The narrower the confidence intervals, the more precise your results are. The more confident you are that the estimate that you have is kind of close to because the confidence intervals are quite narrow. So, I mean, you're estimating 0.8, but it could be as high as 1.3, it could be as low as 0.2. Now, 1.3 and 0.8, it's not that different. I mean, of course, it depends on what the reason. I mean, sometimes, 0.1% can be very important. But, this is a population level estimation. It's a good estimate, it's that it's not very common.
One question, please. In order to calculate confidence interval, do you need to bring information about the prevalence of the disease from other populations or something like that?
Not necessarily. No. You need to know about. It's a bit complicated. You need to know about the variance. You need to know about how much variation there is in your population. You need to know about your sample size, and you need to know about the size of the population. But you can assume that the population is
because
very.
How can I know about the variation on the sample? On the sample, I can.
You can because you have your sample.
Okay.
You have your
from
sample.
the sample, not from population.
Not from the population.
Okay.
I didn't want to go into the
But
math
you
of
need
it.
to know the prevalence and rational inside the big population.
No, you don't need. There's the question that
Not necessarily, no.
you need to know the variation in the sample, not in the population.
We'll get into what factors you need to calculate. I didn't want to.
Okay, but it influences it. The
It does
variability in the
influence-
population
Yes.
Yeah.
influences the confidence interval.
Yeah, of course.
But generally,
If it's a very homogeneous population, whatever
Yeah.
14 people you're gonna get out of
Yeah,
it, you're
yeah.
gonna have the same distribution. Or if it's very, very rare and it's a healthy population, whatever 14 you're gonna get, most of them are gonna be healthy. But if you have something in between with a big variability,
Yeah.
then each 14 can be different.
yeah. So the actual underlying prevalence or incidence of the problem that you're interested in will influence the size of the confidence intervals. So we looked at the prevalence ratio here, and it was 2, and we said it's a small study, and we talked about confidence intervals, and what you could do is you could look at the confidence interval. So you can have a confidence interval around a proportion. You can also have a confidence, we have the prevalence in our 2 groups. You could actually calculate the confidence intervals around the prevalence of coronary heart disease in each group.
Mm.
There's another thing that you can do when you're comparing 2 groups, and that is calculate a p-value. I'm sure you've seen this many times, but it's important to understand what a p-value is and isn't. Now, I don't want to go deep into statistics on purpose, but I want you to understand the context, because it's important for your studies and it's important for the evidence that you see. The p-value tells you the probability of obtaining what you obtained if in reality there is no difference in the 2 groups. Okay? So imagine that you have 2 groups, the smartphone and the not smartphone. The smartphone users and the non-smartphone users. There's a reality that you don't know, that these 2 groups have no different. Generally, we take what's called the null hypothesis. We take the baseline The baseline is that you make an assumption when you do a statistical test that in reality there is no difference in your two groups, okay? So the p-value tells you that with your sample and with the results that you obtain, it tells you how probable it is that in reality what you found is purely by chance, that in reality there's no difference. Well, you'll see an example. And the p-value is directly related to the confidence intervals. And the p-value depends on two things.
So the bigger it is, means the bigger chance you have of finding differences that don't actually exist.
The bigger it is, the
Chance
higher
of-
the chance that what you found is just due to chance.
Okay.
That in reality there is no
There is no-
difference. Yeah, and we'll go into it. We'll see an example. And the p-value depends on several, actually three things, but two things that you really need to remember. The first one is the size of the sample. So the bigger the sample, the smaller the p-value. And this is important because if you take extremely large samples, even if you have a tiny difference, you will find, you will have a p-value that is less than 0.5. So say, for example, you want to do, I don't know, the risk of, just because you're in front of me, the risk of surgical complication of procedure A versus procedure B, okay? And say, for example, in one group, you find 13.1% complication rate, and the other one 13.12%. Yeah, a very small difference. Now, if you did a study and you enrolled 10 million patients in each, not possible, but you would find that this difference is statistically significant. It doesn't mean that it's clinically important. It just it's purely math.
So it's not always good to have a low p-value.
No, you should have a p-value, but the p-value, and we'll come to that. The p-value is a mathematical calculation. It doesn't tell you if it's important. So there's a difference between statistical significance and clinical importance. This is really important because many people look at the p-value and say, oh, the p-value is less than 0.5. Great, it's a good result.
Yeah.
So the size of the sample matters and the magnitude of the effect matters. So if you're looking at two groups and the difference is very big, you don't need a very big sample, right? If you know,
Again, I'm sorry.
the bigger the difference between the two groups, the smaller the sample size you need
To achieve.
to achieve statistical significance. Yeah. So you know, if you wanted to do, I keep taking stupid surgical examples, but if you wanted to compare two techniques.
It's not the surgical example.
No, it's because it's easy. You know, if you wanted to do, I don't know, laparoscopic versus open surgery, you need a certain sample size. But if you wanted to see, you know, using laparoscopy versus using a kitchen knife in survival, you probably don't need a very big sample to show that, you know, being in a surgical room with anesthesia and proper tools gives better outcomes. Well, probably a couple of patients is enough, right? So the size of the effect. You know, if you have mortality of 100% on one side versus 0.1% on the other side.
That makes sense, but what you said before, that's new information to me, that actually if you have a too bigger, I don't know how to say, too much bigger size than you need, you might have a statistical significance, but it's confusing because it doesn't really.
So we'll talk about.
That's the other side of the other side of the coin. If you have a big sample size, even very small differences will
Becomes
achieve
big one.
statistical significance. But if it's a very small,
But then you have to take
Then-
into
then the
account, okay,
point-
it will happen, it will be significant if you treat 10,000 people with this medication, one of them will have,
yeah.
so that's the need.
So we'll see exactly, and we'll see how it applies in real life. And generally, we use a cutoff in most clinical studies. We use a cutoff of 5%. Our accepted threshold is that if there is less than 5% chance that our findings are due to chance, that there is less than 5% that really there's no difference, and 95% chance that there is a real difference, that is acceptable. There's nothing magic about it. You could choose, you know, if you wanted to do in quantum physics, they use 1 in, I think, 1 in 100 million, like p less than 10 to the power minus 9 or something. It depends on the field, and it also depends on the particular question that if it's a really, really important thing, you might want to choose a lower threshold to really be sure that what you find is
Yeah, a lot of times they use P lower than
0.001.
0.01.
Yeah, absolutely, yeah. But generally, but it's not a magic number. This is also important to know.
In which situation you can use higher error, like
Higher, it would be very, very rare. You would, I've
like point 0.1.
well,
Instead of 0.5.
If you wanted to do a say, for example, you were going to, I don't know, you develop an approach that, you know, and you want to roll it out nationally, and it's going to cost hundreds of millions of shekels. Before you invest in it, you want to really, really be sure that whatever you're offering works, right? A new treatment as a new standard, for example. You might want, you know, a small study with a p-value that is very close to the threshold may not be enough. So you may want to. So let's go back to our amazing study that is not going to get into the Lancet. The use of smartphone in coronary heart disease. So we did our prevalence in each of our groups. We did our prevalence ratio of 2, and we calculated the p-value, and the p-value is more than 0.25. Okay, so what does that mean?
More than 25% chance that this is accidental.
Exactly. So there's 1 in 4 chances that what you found that the smartphone is associated with coronary heart disease is not a real association. It's purely due to chance. That in reality there is no difference. Now, if you're going to make a decision on your patients, you know, to ban all smartphones in the world, 1 in, you know, it probably doesn't give you the confidence to do that.
So again, first we have to understand what is the chance that my results are by a chance,
Yes,
or more valid. This is the P, and then we have to understand what's the significance. Like, okay, I have a good validity, but
so
the
significant.
results are significant only when we compare 10,000 people with one another. So clinically, it doesn't mean anything.
Exactly. So you have to be,
because the disease is more dangerous than the
significant. Yeah.
immunization. That's it.
So this is why if you ever co-author with me or give me papers to correct, you will see that if you use the word significant has a very specific meaning, which is generally associated with statistical significance. It does not mean that your finding is important or clinically relevant.
Right.
Okay? It's just
but
based
that's
on
how
an
they
equation.
Play with the results because they show you all these tables.
Yes.
P, but what's the meaning?
Exactly.
That's why I wouldn't be a devil's advocate to say that this can also be viewed as there's a 75% chance that this is not accidental. So it might not have reached. This sounds like a stupid question, but if the p-value was 0.06.
Yeah.
And I think that this might be, there's a 94% chance that that this is not accidental, right?
Yeah. So you're absolutely right. Again, there's nothing magic about 0.05, and not reaching statistical significance doesn't mean that there's no effect. It could mean that there's no effect. It could mean
trying to be conservative and not change our practices based on.
So what it means, if you really believe that you're onto something, what it tells you with the 0.06 is that your study is not big enough, right?
Because in basic research, when I did basic research in Berkeley, in basic research they do look for. It's very important.
It is important
because it's another question. When you have clinical question, you have to think about the implications of your treatment.
It is important in clinical research.
Side effects, and then you have to consider if you want to take a chance of 1 to 10,000 for something or not. Or what's the cure versus the disease, what the chances of that and that. in basic research, you do want to know if you have that effect.
It's important.
It's more
What I'm
clean
saying is,
question.
it's important in clinical research. It's just not the entire
No,
story.
it's important, but you have to take it in context.
Correct.
In basic research, it's more clean research. You have a question.
It can be cleaner, yeah, because you don't
It's
have.
cleaner, you don't have all these
Yeah.
considerations to
Yeah,
take.
yeah. Cells and
Either it
bacteria
works or
don't
it
have,
doesn't work, like on the
yeah.
cells in the dish. It works or
No,
not.
but there is still, I would partly agree, but not entirely that it's the entire story.
Cleaner, not.
It is cleaner, yeah, yeah, absolutely. And we'll come to what you're talking about is a lack of power in a study, which we'll come to. So, you know, this is a study that I did actually a few years ago, looking at the association between ethnicity and vaccination in the UK, right? So you can see I've just circled one example, which is comparing the proportion of this is pregnant mothers vaccinated with the pertussis vaccine, the proportion of Black African mothers compared with the baseline white British population. And what you see is that compared with the white British, sorry, the Black African mothers had 10 percentage points lower vaccine coverage. And you can see the p-value, and what the p-value tells you here is that there is less than 1 in 1,000 chances that this finding was due to chance.
Okay.
It doesn't tell you that it's not due to something else. It could be due to bias, it could be to, exactly. And you can see the confidence intervals are quite narrow as well. Right, so this is what a p-value tells you. It still doesn't tell you that your result is causative. It just tells you that it's very unlikely that you found this just by chance. Also because the samples are very large.
So, yeah, it's statistically significant, but it might still be that Black Africa, that something else influences
Could be confounding. It could
where
be
they
that.
live. Maybe in this neighborhood, there are not enough clinics to vaccine. So it doesn't
Exactly.
mean that it's because they're Black. It might be because other things
Exactly.
that
Exactly.
we didn't
Exactly.
investigate here,
Well,
but
yeah,
it's
I mean,
not by chance.
We did, but I
No, I
didn't
mean-
tell you about it. Yeah, yeah, exactly. Absolutely
Only
right.
this table. It
So
means that
always remember,
Black Africans most likely are less vaccinated than white people.
also know they're more
It might be not because they're Black.
socioeconomically deprived. You know, there may be all
They
kinds of
don't know
different
enough
things.
about it.
Could
they
be,
don't have
yeah,
enough
yeah,
physicians.
exactly, exactly. So remember that the p-value only tells you about chance. It doesn't tell you anything about bias, and it doesn't tell you anything about confounding. We'll come back to
But you
that.
have adjusted for some confounders, no?
I have. We'll talk about confounding later. Of course I have. Like if you did a study like this without talking about confounders, it wouldn't be a very good study, right? So how do I know, coming back to Khovar's question, how do I know if my sample is big enough? Because the last thing you want is to start a study, you know, you found this amazing new technique and you think it revolutionizes the, you know, post-op infections, and you have a great result, but it's not statistically significant because you realized you should have recruited an extra 30 patients to have the. So you need to know this before you start, right? How do you know that your sample is big enough? Well, so when you conduct a study and measuring the difference between two groups, which is what most of you are doing, you want to make sure that the sample size is big enough to detect a difference if there is one. Because if your sample is too small, your results actually may not show that difference, whereas there's a real difference in the population. So this is what you're talking about. So if you're finding no statistically significant difference, you can actually, it could be due to two things. It could be because there is no difference, or because there is a difference, so it's your study is not powerful enough to detect it. And if in epidemiology, this is called a type 2 error. A type 2 error is a failure to identify a difference when there is one in reality. And it's due to statistical, to the size of the sample.
And power depends on what? On the size of the sample?
It depends on three things that we're gonna see in a minute. So let's take another example here about power. You want to imagine you're doing a study looking at the association between obesity and cholesterol levels, right? So your hypothesis, well, you have two groups. You have people with a BMI of less than 25 and people with a BMI of more than 30, and you measure the mean LDL. And you find that in your very small study of 6 people in each group, you find that among those who have a normal BMI, the mean LDL is 92, which is the normal value. And in those who are obese, mean LDL is 106. Okay, so you have a difference in mean cholesterol levels of 14 milligrams per deciliter. If you do the math, which you can do with a simple sample size calculator or a p-value calculator, in this particular example, p is 0.13. So you cannot exclude the fact that the difference is purely due to chance. Maybe there isn't a real difference. It's just that your sample is small. Maybe it's just normal variation.
Other 6, it would be another difference.
Well, let's not try another 6. Let's try multiply by 10. Yeah? Now you're finding that in your two groups, you have exactly the same mean value, but now there is less than 1 in a million chances that this difference is due to chance. Okay?
Because it's consistent in bigger numbers.
Because it gives you the confidence that your sample is big enough to detect that difference.
Also, the variability within each group matters because you have 29 and 106. But if the variability is very, very big, so they have parts where they are overfilled.
You want to do the lecture, Dana?
Overlapping.
They're overlapping.
You want to do the lecture because this is my next slide.
Oh,
But you're absolutely right.
Sorry.
That's called a
Sorry.
It's actually called the variance. The proper word is variance. So there's 3 things that matter. The first one is the sample size, and we talked about it. The second one is the size of the difference in the measured outcome. So if one group had 30 milligrams per deciliter and the other one had 250, you would need a much more sample size. And the last one is the variance or the standard deviation, which is a measure of how spread the results are in your population. So, and this is, it's a little bit complicated, but imagine you take 100 people and you measure their LDL, and the mean value is, we saw, 92. If everyone is very, very close to the average, you need a much smaller sample size than if the results are very, very spread. Yeah, so you can imagine like a normal distribution curve, you know, these curves,
Right.
with the mean in the middle.
The two of them are narrow, they're different.
The more narrow,
The two of them are like that, so it's not, there's a lot of overlap
Exactly.
between the groups.
exactly. So these are the 3 things that really determine how many people you need. But you don't need to worry about having to calculate standard deviation, because when the statistical packages will do it for you, and working with a statistician that will help you, or you can find calculators online and you enter all your data, it automatically calculates it. But it will tell you whether
that after you have the results. But how do you plan your size, the size of your samples if you don't know in advance what will be the results?
the variance generally you don't know, but the sample size you can
the
know.
standard deviation and the average. That's what you're looking for.
Well, but you can find some things, like for example, you generally as a clinician you will have some kind of how do you call it, like informed guess.
Okay.
You're not completely, there's literature, there's other studies, there's surveillance data. You will get an idea, you will get some idea. You're not operating in a vacuum. I agree that if it's something completely new that there's nothing on, it's difficult. It's difficult.
The sample size calculator. I don't remember that it requires me to put in like
It will.
It asks for the sample size and
It depends.
Ask for the size of the measured outcome.
I'll show you a sample size calculator in a minute. If you enter in your line by line data, if it's asking for the value of each of your patients, then you don't need to enter the variance.
No,
right?
I'm talking about the sample size. Before you do the research, you don't have values for your patient. You have measured. If you want to see your sample size, it doesn't ask.
If it doesn't
ask me for.
If it doesn't ask you for a variance, it will assume a certain value. It will assume it in the background.
Okay.
Right? So what's the difference in sample size and power? Because sometimes you hear, oh, we need to do sample size calculation. And sometimes you hear, oh, we need to do power calculation. And it's basically two ways to think about it. Because there's two different things you can do. You can say, well, I want to detect a certain size difference between my two groups. And if you know that, you can calculate how many people you need to recruit to achieve that. Or it could be the other way around, which is more common in clinical research, which is, these are the patients I have. You know, you have your clinic, you can't recruit more people that you have. You know, you have 25 breast cancer patients, that's what you have. What can I detect with that? And that is called a power calculation. And often in observational clinical research, you are limited by the number of patients you have. If you're doing randomized controlled trials, you actively recruit patients. If you're doing observational research, generally you have what you have. If you don't have enough patients, then there's different things you can do. You either have to change the outcome that you're looking at, or you need to work with other hospitals or find partners to increase the number of patients.
And when you do a systematic review or meta-analysis, do you take the results of each study, or do you pool the patients, like all the one with the intervention and all the one and then compare them?
In a meta-analysis, yeah, you pull the data. So if you look at a meta-analysis, you will see that each study, when you look at your final plot, your forest plot, has confidence intervals around it, which tells you generally how many, it's an indication of how many patients were recruited. So the weight of each study will depend on that.
When you want to pull a few papers together,
Yeah.
to have stronger results, so do you compare the results from each paper based on the size, or do you say, let's take all the patients without intervention from all?
It's the same thing.
It's the same thing?
Yeah. It's the same. Right. So in some circumstances you will calculate sample size. In some circumstances you will calculate power. So if you have a very large population that you can choose from, you know, if you're choosing CT scans and you have or PET scans and you have tens of thousands, maybe you don't need all of them. You can look at how many you need to achieve what you want. If you're doing a study with you have access to relatively few patients, then you think about it the other way, which is, what can I detect? What size of difference can I detect with the patients that I have? And you can see that this thinking applies to measuring differences between groups, but also just single groups to look at precision, which is the confidence intervals. So here's an example of a sample size calculator that I just took online. If you want to compare two groups, it needs the level of confidence that you want, the power, and the power is the probability that you will detect a difference if there really is one. And generally the accepted level for that is 80%, generally. But again, if you wanted to be really, really sure, you could increase that. But the more you increase it, the bigger the size of the sample you need.
So that's your notion in the beginning. What is the hypothesized difference? So that's based on literature or your experience?
Correct.
And what is the population variance? It's also, those two are based on what you feel or know.
Yeah. So generally, when you're comparing groups, what really matters is not the variance of each group matters, but it's more that if the variance in the two groups are different. And in a lot of the calculation, it will make the assumption that the variance is not different, that the variance is the same as in the two groups. So if it doesn't ask, that is the baseline assumption, which if your samples are big enough, is generally holds true. If you have very small samples, not so much.
But your recommended sample size is 157, but doesn't say how it breaks down.
No, this would be 157 in each group, I think.
What does that mean, the number 1000 in the variance?
In this particular example, I don't exactly know the variance you calculate based on the spread of the variable of interest in your population.
So you're saying that this calculator offers a sample size when you predetermined that you want the groups to be equal size.
Yes, correct.
So when will you choose groups of different sizes?
You can choose groups of different size to increase so you can increase the power of your study by including, say for example, in some instances, it's much easier to recruit controls than cases, right? So you can instead of recruiting one control for each, say for example, you want to find out the effectiveness of a particular intervention, and you have your standard treatments, right? If you recruit the same number of people having the standard approach versus the new approach, you will have a certain power. If you recruit more people in this group, you have more power, and generally up to 3-4 controls per case, it will increase power, less and less each time, and after 4, really it becomes a waste of time. But you can do this to increase power, because sometimes you just don't have that many cases or that many people exposed to, like say for example, you're doing a national study of, I don't know, robotic, using the robots to do a bladder, to remove the bladder. I can't remember what name. The Da Vinci, exactly. Thank you. If there's one in the country, you're only going to have so many people operating on that versus a normal cystectomy, which you can recruit many, many, many more. So you might have unequal group sizes in that kind of situation.
I mean, the sample size, it means every group should be one.
Yeah, I think I just took it from the internet. I mean, this is not good. Really, what they should tell you, if it was a good website, they would tell you you need so many cases in this group and so many cases in this group.
Yeah.
But it's the principle that I want you.
For sure, but I think it asks you what you want to do. If you want same size, or you want.
Yeah, it gives you different options. It gives you different options, and you can generally play with the size of the. If you're doing the other way around, which is the power, the power calculation. If you say, how many patients in group 1 you have, how many patients in group 2 you have, what is the size of the, and then it will tell you what size of a difference you can detect. Right? I've given you a little bit of a simplification because there are many other things to take into consideration. The underlying distribution of the population, whether it's normal, non-normal, whether the observations are independent or dependent, which I don't want to go into. Bottom line is, it's important for you to understand the basic principles, but I would recommend that you speak to a statistician or an epidemiologist when it comes to this, or someone who has experience in designing studies, which is why your mentors can help as well. This is my favorite. I love this. I actually took this picture from a lecture that I had 15 years ago. The P less than 0.05 is not God. It is not an absolute thing that you base your decision on. It's an important thing, but it's not the only thing. And it only tells you about chance. It doesn't tell you anything about bias. It doesn't tell you anything about confounding. Okay? So it's important that you exclude chance, but when you read a paper or when you do your study, remember that just because you hit this magic number doesn't tell you that.
Yes, sometimes it seems like it's everything.
Exactly. And it's not. So now let's talk about bias and confounding. Right. So chance is basically random error, right? It's by chance you find things or you fail to find things. Bias is a systematic error. Bias is basically anything you do in the collection, the analysis, the interpretation, the publication of data that leads you to conclusions that are systematically different from the truth. Do you want to break, or are you okay to continue? You want to continue, or you want to take a? Okay. So we'll start bias in a few minutes then.
Okay, breakfast is ready.
Thank you.